In the previous class, we looked at the solutions for Maxwell's equations in a homogeneous, isotropic, unbounded medium, and we saw that if the cause that is producing the fields is time varying in nature, even the fields will be time varying. And we said that we also said that the way the electric and magnetic fields exist is in the form of a wave. So we had said that because we came up with something called the wave equation, which was this is for the electric field and this is for the magnetic field. So we saw that the nature of these is very similar to what we get for voltage and current on a transmission line. But we had ended the last class saying that while it is very easy to solve for V and I in general in a transmission line, same cannot be said for the wave equation because the fields exist in 3D space. So what are the components, the XYZ components of E and H, and what are the way in which they exist? That is something which we need to ask ourselves. So we had said that we shall examine some standard solution forms and see whether those solution forms indeed work or not. So let us try out something. So let us take case 1. When the electric field has constant magnitude but is time varying. So I can say it could be something of the form of some constant times e raised to j omega t. You can simply take a look at this and say that no, this cannot be the solution, because immediately you can see that there is no space variation. So therefore the space derivatives would become 0. So therefore this cannot happen. Now let us take case 2. One possible nature of the electric field vector could be that it will exist only along one axis and be a function of that axis. So for example, it could be something like this. Let us say the electric field vector exists along the x-axis. So therefore the x unit vector will come. It has to be time varying. Of course, that is there. We have established that time varying has to be there, without which we cannot have the fields. So this is there, and we said the E will exist along one axis, which is x, and also be a function of that axis. So let us say E is some function, let's call it E0 of x, which also exists along the x-axis. Now what do you think? What do you think? Will there be a corresponding magnetic field along with this? No, there won't be. Because if I try to apply Faraday's law and take the curl of this vector, you will immediately see that the curl is 0. Let's see how it is. So I can say curl of E So here I have the x derivative, y derivative and z derivative. I can immediately say that when I am solving for the y component, it will be dz of e of x, and we said that is varying along x axis only. So therefore this differential will become 0. Similarly, the y derivative of this will also be 0 because E0 is a function of x only. So therefore this would identically be 0. So magnetic field cannot exist. So two cases we saw. Constant magnitude but time varying is not possible. And one field existing along one axis and also be a function of that axis is not also correct. So therefore both of these are incorrect forms. Now let us take case 3. We are going case by case basis is because we are looking for the simplest solution. Once we know the simplest form of solution, and that is what we will apply, because we said that some of the best solution forms by nature are simple. So therefore there is no reason why that cannot exist. So now let us take case 3, where the electric field or any field, let's say the electric field, exists along one axis but is a function of another axis. So as always the time varying part has to be there. So now we can say this E exists along one axis but is a function of another orthogonal axis. Say for example, if E exists along the x-axis, it could be a function of the z-axis, for example. So let us say exists along x-axis but is a function of z only. It's very much possible. So the form of E would be something like this. Since it exists along x, I will put the x vector. It is time varying, so I will put this e raised to j omega t, and the magnitude function is some E0 of z. So this is one form which we can investigate. Now let us see whether the H field will exist or not. Let us take the curl of E. What we will see is essentially this. So oh, I'm sorry, this should be over here because it is variation of, it is variation with respect to x, so therefore this should be over here. So what do we get now? We know that E0 is a function of z only, so therefore these two essentially become null. So therefore the determinant now looks like this. So now this will simplify to something of this kind. Now when I am taking the determinant, the only non-zero determinant will be when I am taking with respect to y. So So this is what it will be with a minus sign. And that is nothing but, as per Faraday's law, it should be nothing but minus mu times dH by dt. And as we know, we have proved in the last class that this is nothing but an operation j omega. So therefore I can rewrite this as nothing but minus j omega mu times h. So therefore I can say h vector, I can simply cancel these out, will be nothing but 1 by j omega mu So now we have got what looks to be a solution. What we said was that the electric field would exist along the x-axis but be a function of z. What we are seeing is a non-zero magnetic field exists which is a function of y. So just like how we had an electric field with a non-zero x component, so what we had said, this implies that Ex is non-zero and Ey and Ez is 0. What we are seeing is we are getting a magnetic field where Hx and Hz are 0 and Hy is non-zero. So in some sense, the electric field direction, the magnetic field direction, and the way the electric field exists, the function of the electric field, they are orthogonal in nature. Now this is probably the simplest solution. So now, yeah, I think just a small thing, there will be no minus over here. I just realized if you take the determinant, this will still be a plus. So this minus would still be there and this would carry over here. Not that it's very important, but still for the sake of completion, this should be there. And that's how it is. So just to repeat, we found the simplest possible solution where the electric field exists on one axis, is a function of another axis, and the magnetic field is a function of the third axis. So in general, we can generalize it for any axis. So even if E were a function of y and varying along x, you would see that h would be varying along z. So that's the beauty of this field behavior. So what the electric and magnetic fields essentially you can see are in some sense orthogonal. Now we have found out one solution for the wave equation where we are seeing that we have this electric field x which is a function of z, we got magnetic field y which is a function of z, and this exists along x direction, this exists along y direction. So this is in some sense a wave because it satisfies the wave equation, very similar to a transmission line. So therefore this solution is called as a uniform plane wave. Why it is called uniform and plane, we shall see that shortly, but this is what it is called. So now we know that our solution or our simplest solution only needs that E and H be on one axis only. So this makes our analysis a lot simpler. So therefore, if I now put the wave equation back, which is nothing but this for the electric field, I can simply say that the Laplacian operator on the different axis. So now, right now I am doing away with the vector notation because I know that since the electric field exists only on one axis, I can simply say this I can put. Now there is no need to put any vector notation because for electric field this condition must be satisfied. So now remember, Ex is a function of Z. So therefore this and this would cancel out. What we would have is d square by dz square is nothing but minus omega square mu epsilon times Ex, which is also a function of Z. So now what we are seeing is that we now have a single dimensional solution for the wave equation. And now this is very, very similar to the voltage solution on transmission line. For lossless transmission line, we know that d square v by dx square is nothing but minus beta square v. So these two are now all but identical. So I can say Ex as a function of Z using a solution which is very similar for this differential equation is nothing but sum Ex plus times e raised to minus j omega under root mu epsilon times z plus Ex minus e raised to plus j omega under root mu epsilon times z. So this is very, very similar to a solution of the transmission line equation where we had Vx plus and Vy minus. So again what we are seeing is, in general, there can be two waves, one going towards positive z direction, the other going towards negative z direction. So now just like how we now are seeing the solution for the electric field vector, we saw that it is a similar nature with the voltage solution for transmission line. Now what we can say is that just like how we had analyzed different quantities of a transmission line, let us now do the same analysis for this wave. Now, in general, if you remember, the transmission line gamma was alpha plus j beta. So it had some real part and some imaginary part. But for a lossless line, if you notice, the V of x was something like this. So over here, for lossless, we have alpha equal to 0. Now what we are seeing for our electric field as a function of z is something of this kind. Even over here, the power of E is imaginary, because the medium that we are assuming is purely homogeneous. There is no charge, there is no conductivity, there is no conduction current. So this shows the conductivity, the charge density, the current density, they are all 0. So therefore this is the equation in a lossless medium. So now if I try to correlate the exponential terms, I can say that the beta of a transmission line is in some sense equal to omega times under root mu epsilon. So as we know that the angular frequency omega is nothing but beta times the velocity. So that means the velocity of the wave is nothing but omega by beta, which is nothing but 1 by under root mu epsilon. Now for free space, mu equals mu 0 and epsilon equals epsilon 0. So if you substitute, what you will get is that the velocity in free space is nothing but 1 by mu 0 epsilon 0. And if you substitute the values of mu 0 and epsilon 0 that you very well know, you will see that this value is almost equal to 3 into 10 raised to 8 meters per second, which is nothing but the velocity of the electromagnetic wave in free space. So today we have proved a very important result. We have seen that the equation, the expression for the solution for the wave equation is nothing but a pair of waves which are very similar to a pair of waves on the transmission line. And using that same theory, we saw what is the velocity of the wave. Now in general, for any medium, so which can have mu r and epsilon r, which are the relative permeability and permittivity, we can write the velocity as nothing but 1 by under root mu r mu 0 times epsilon r epsilon 0, which can now be written as this. So this quantity we already know is the velocity of electromagnetic wave in free space. So we can write this as C by under root of mu r epsilon r. So where C is the velocity in free space, which is equal to 1 by under root mu 0 epsilon 0. So this is a very important result. Now if I have the solution for E of x as a function of z, which is nothing but Ex plus times e raised to some minus j beta z. Let us now call this omega under root mu epsilon as beta, and no need to write the full term anymore, plus Ex minus e raised to j beta z. Now just like in transmission line, we started with voltage and then we try to calculate current. Now let us start with electric field and try to calculate the magnetic field. So we had proved that for Ex, which is existing along the x direction but as a function of z, you will have Hy, which is also a function of z. And that, as we proved just few minutes back, was something of this kind. So let us put that. That is nothing but minus 1 by j omega mu, the z derivative of Ex of z. So if I now substitute this term, what I will get is minus 1 by j omega mu. I will take the z derivative, I will get minus j beta Ex plus e raised to minus j beta z plus j beta Ex minus times e raised to j beta z. So once I open the bracket, the j and j term will get cancelled out, and what I will get is nothing but beta by omega mu Ex plus e raised to minus j beta z minus beta by omega mu Ex minus j beta z. So this is what the magnetic field intensity nature looks like. Now don't forget that this is along y direction. This vector sign is implicit. We have not put it so far, but this is the way it is. So that is what it is. So now let us then rewrite the solutions for E and H. So Ex as a function of z is nothing but Ex plus e raised to minus j beta z plus Ey minus e raised to plus j beta z, and Hy as a function of z is nothing but beta by omega mu Ex plus e raised to minus j beta z minus beta by omega mu Ex minus times e raised to plus j beta z. Now we know that over here beta is nothing but omega under root mu epsilon. This is what we know. So we can substitute over here. This quantity beta by omega mu would become omega. So this would be nothing but under root mu by epsilon. So therefore H of y Hy of as a function of z would be something of this kind. Let's write it this way. So now let's call this as equation 1 and this as equation 2. What are we seeing? We are seeing that just like a lossless transmission line, the expression for E is following voltage and the expression for H is following current. So if you remember, current expression was something like this. This was for transmission line. So likewise for E and H fields, we do have something in the denominator also. So you can immediately see that the unit for mu is nothing but Henry per meter and unit for epsilon is Farad per meter. Now if you remember, for a lossless line, Z0 was what? Under root L by C, where even L was Henry per meter and C was Farad per meter. So now what you see is that they are identical. So what I have for mu by epsilon is very, very identical to the ratio of L by C under root for the transmission line. So what is the unit of Z0? The unit of Z0 is ohms. So even this ratio under root mu by epsilon, because the units are same, will also have the unit of ohms. So therefore this also indicates some impedance which is the property of the medium. Since Z0 is called as characteristic impedance, this impedance is denoted using eta and is called the intrinsic impedance of the medium. So that means just like how Z0 is not a physical quantity but it exists along the line, the intrinsic impedance of the homogeneous medium, which is unbounded and infinite, this impedance does not exist at a point. It is a distributed impedance. If visualization of Z0 is difficult, visualization of eta will be even more challenging, if not equally challenging. So this is called as the intrinsic impedance. So what is happening? Now let us look at this intrinsic impedance a little more closely. Just like how we had calculated the velocity of the wave in free space, we can also calculate the intrinsic impedance of any medium, or let us say free space. So eta will be nothing but mu 0 divided by epsilon 0. So now if you substitute the values you know for mu 0 and epsilon 0, you will see that the intrinsic impedance of free space, you can find this out yourself, is roughly about 377 ohms. So if you treat space as a transmission line, the transmission line will have a characteristic impedance of 377 ohms. Now let this sink in. In our analysis so far, we have been dealing with 3D quantities. But what we are seeing is that at every step, we are trying to correlate it with a 1D phenomena, that is a transmission line. The fields may exist wherever possible, but in case of the solution for the fields, they are behaving in pretty much the same way in which voltage and current on the transmission line behave. So we derived what is the velocity of the wave in a medium, we derived what is the intrinsic impedance of a medium. So for any other medium, the eta is nothing but mu r mu 0 by epsilon r epsilon 0, the whole under root, where these two are the relative permeability and permittivity. So now this is a very important result. So what we see? We had seen that for a lossless transmission line, the Z0 is always real. Likewise, for a homogeneous lossless dielectric medium, the eta or the intrinsic impedance will also always be real, because there is no concept of alpha. Now, let us come back to the field equations or the solutions for the fields from the wave equation. So what we are seeing essentially is this. If you rewrite, it's Ex of z is nothing but Ex plus times e raised to minus j beta z plus Ey minus times e raised to plus j beta z, and Hy, which is a function of z, is nothing but Ex plus times eta. So now we know that this quantity is eta, so let us write it that way, times e raised to minus j beta z minus Ey minus by eta e raised to plus j beta z. So sorry, this should be x. This should be x. So what we can say? This and this denote wave traveling in the plus z direction, and this denotes the wave traveling in minus z direction. So what is happening if I am drawing the three axes? So as you know, this is x, if this is y, then this is z. What we are seeing is that the electric field vector exists along the x direction or the x axis. The magnetic field exists along the y axis but is a function of z, so is the case for Ex. And the wave is essentially propagating either here or here. So depending on which wave you are looking at, one wave, this wave is going in the positive direction, this wave is going in the negative direction. So therefore we know that the electric field is nothing but, in this case, the Ex times e raised to j omega t times the x vector, and h is nothing but hy times e raised to j omega t times the y vector. So therefore, these will exist as sinusoids. So something of this kind. This is how the electric field vector will behave. This is how the magnetic field vector would behave. They would be like two orthogonal sinusoids. So this is how these sinusoids will oscillate and the wave propagation will be either here or here. So this is one way to look at it. So this is the E vector, this is the H vector, and the direction of propagation is orthogonal. So now remember what we had called this wave. We had called this wave as a uniform plane wave. Because now if you look at this, if you place your eye over here and look at the wave, it seems as though the electric and magnetic field, they are sort of oscillating on the xy plane while the wave is traveling along the z-axis. So therefore, the wave, the field vectors are sort of existing and time varying along a plane. So therefore, this wave is called as a uniform plane wave. So that is one way to look at it. Now, since the nature of the fields are sinusoidal, because the nature of the cause that is producing it is also sinusoidal, these waves are transverse in nature. So this wave is also called as a transverse electromagnetic or TEM wave. So what we are seeing is that by correlating the forward waves, electric and magnetic components, and also correlating the backward waves, electric and magnetic field components, we can show that Ex plus by Hy plus is nothing but eta, and Ex minus by Hy minus is minus eta. This is very similar to the transmission line where V plus by I plus is Z0 and V minus by I minus is minus Z0. So that is the solution. So since what we see is that the relation between the field components is governed by the intrinsic impedance, this solution is valid for not just at the origin or at some point, but every point in space and time. So now what we are seeing is that in the previous page we drew the Cartesian axis. We said that if electric field is varying along this x-axis and magnetic field is varying along the y-axis, then the whole propagation will be along the z-axis, either this way or this way. But in general, this need not always be the case. The definition of our axis can be anywhere. Now let us say, for example, we are saying that my electric field is existing over here and the magnetic field is existing over here. So now we saw that one possible direction of propagation is over here. Now let us say when both electric and magnetic field are positive, they will exist in this direction, because the reason why I am saying positive is because The E and H, they are sinusoidal fields, so never forget that. They have that j omega e raised to j omega t term. So when H becomes negative, it might go over here. When E becomes negative, it might go over here. So now what's going to happen? Let us assume that there is a time when E and H are both positive. Let us now look at the E vector, H vector, and the direction of propagation as a relation of directions. So if I now use my right hand thumb rule and I curl my fingers from E to H, then what I am seeing? The perpendicular is giving me the direction of propagation. So direction of propagation of wave is nothing but the direction of the vector product of E and H. So if I were to take the vector product of E and H, I would get whatever be the magnitude, but the direction would be the same as the field propagation or the wave propagation, sorry. So now if they are both negative and I curl my fingers, you can again see that it would give you some direction, whatever that may be. So now it may so happen that at one point E may be positive and H may be negative. So in that case, let us look at that. If E is positive and H is negative, if I curl my fingers this way, my thumb is pointing to the paper. So therefore in that case, the wave will travel to the inside the paper, opposite direction. So what we can see is that using one result that we already know, we can sort of apply the directions to predict which wave or which way the wave will propagate. So now I was mentioning that in general the E and H field vectors need not always be aligned on the x and y axis. For all you know, they could be existing anywhere on the x and y plane. So let us see how. Remember that we are taking E and H along the x and y directions because that is what the simplest solution for the Maxwell's equations or the wave equations gave us. In general, we have now proved that even if I want this wave to travel over here, any two orthogonal E and H vectors would give me a wave which is traveling on the z direction. Now, the nature of those E and H fields may be something more complex. That's okay. But we should not close our eyes to the fact that such fields can also exist. So let us say this is x-axis, this is y-axis, this is z-axis. Now, in general, I could have an electric field which is like this. This could also be sinusoidally varying. But now, this could be some function of the Cartesian axis. But in that case, the magnetic field should be perpendicular to the E field. So then in that case, I can tell you that this E vector is lying on the xy plane and even this H vector is lying on the xy plane. So even then, if I now take the cross product of E and H, my thumb will still point to Z. So I can still say that the direction of propagation can be either here or here, but along the Z direction. So this is something which is very interesting to note. In general, the fields can be like this. So one of the reasons behind the discussion is, or the discussion behind telling you that the E and H fields can lie in any direction, need not always be along X and Y, is because that is what happens for most cases. Not always is that the axes that we define are the same as the direction of the E and H fields. So in general, once we know any of the fields, either E or H, we can easily find out what is the other field. So once we know, let us say E, we can easily find H using Maxwell's equations. So, or vice versa. Or vice versa. So, means if we know H, we can find out E. So, for example, we had taken when we were finding the solution for the wave equation, we had taken one form of E and we applied the Faraday's law to get H. Similarly, if we know H, we can apply Ampere's law and get E. So now it is important to note that the E comes from H or the H comes from E, but the E field vector exists using displacement current density because we are talking of a homogeneous medium. So this is one example of how waves travel in a homogeneous medium even when there is no physical current element. So as you remember, we had made rho, sigma and J all equal to 0 because we are talking of a homogeneous medium or a dielectric. So now coming back to this statement that once we know E, we can find out H. This is a very important statement. So now we can say that if we know E, and we know, let us say, the direction of propagation, we can find out what is H. So looking at the E vector can often give us a lot of information. So let us look at that. So now let us say that on the xy plane my E vector is over here. Now in general, when I am placing myself over here, when I am looking from here, this is my eye, and I am looking vertically on the xy plane, that is through the z axis, then I can see the E field vector on the xy plane. So let us see it how. Let us now say that this is my two axis x and y, and my z axis I am going to show in this format because, as you know, this means coming out of the plane of the paper. And why I am drawing this? Because this is the way I am looking. So what we can do is, even though the electric field need not be aligned with either x or y, we can definitely have projections on the two axes. We can have a component called Ex and Ey. That is definitely possible. So the magnitudes need not be equal, neither need the phase, because remember this E field vector is now oscillating. Now if I am looking from here through the z axis, and what I am looking at is only at the tip of the E field vector. The way it is changing, the way the position of the electric field vector tip changes with time is called polarization. The locus of the E vector tip with time is called polarization. That means which way is the wave oriented. That is a very important relation. So polarization can often be more easily understood if you take the vector and project it on the x and y axis. So therefore in general we can write that Ex is some E1 cos omega t. You can assume that it is, we can take the real part of the e raised to j omega t, and Ey in general could have a different magnitude E2. It could also have a different phase, but same frequency. Let's say this small delta is the phase. So now I can say that cos omega t is nothing but Ex by E1 and cos omega t plus delta is Ey by E2. So what we can do now, we can expand this cos addition term. So as you know, cos of a plus b is nothing but cos a cos b minus sin a sin b. So expanding, we get this is nothing but Ey by E2. That's what we have defined. So we know what is cos omega t. Cos omega t is nothing but Ex by E1. Now once we know cos omega t, we can find out sin omega t also, which is nothing but 1 minus cos square omega t, the whole root. So this is nothing but, I can say 1 minus cos square omega t, which is Ex square by E1 square times sin delta. So now if we take the square of this expression, we can say that cos of omega t plus delta is nothing but Ey by E2. So if you take the square of the left hand side as well as this side, you will get some result. So let us do that. Ex square by E1 square cos square delta minus 1 minus Ex square by E1 square times sin square delta. Oops, I made a mistake. This should be the square of the whole term. So what I can do, I can easily take this on the left and this I can take on the right. So this would become 1 minus ex square by e1 square times sine square delta is nothing but this minus this whole square. Sorry, this minus this whole square, because once so now let us expand this and rearrange the terms, which will give us something of this kind. This is what you get. Now E1, E2 and delta are fixed. What changes is Ex and Ey as a function of time. So remember what we are trying to do. We are trying to see the E field vector projections on the x and y axis as a function of time or the polarization. So now if you look at this equation and I am trying to draw this equation graphically on the xy plane, what this will look like? This will look like an ellipse. This will look like an ellipse. If you remember your conic sections from high school, you can see that this will behave like an ellipse, because you in general you have two different square terms, and that's how it is. So now if I were to draw this, and as always I am looking from here into the paper, I am looking vertically on the paper, what I will see in general is something like this. It could be oriented anyway, but that's not a big deal. But this is the locus of the E field vector. And so in general what will happen is the E field vector will rotate like this. As a function of time, it may go this way or this way, whichever way is possible. So with time, the orientation of the electric field vector also changes. So this kind of a polarization is called as elliptical polarization. And this is the most general case of all polarizations. So in general, what we derived, that expression without any other conditions, comes out to be an ellipse. So in general, all polarizations are some form of elliptical polarization. So now what we derived was this equation. So this is the equation for general elliptical polarization. So what is important to note is that with time the electric field vector tip will trace out this path. Now this may seem a little too close to home or a little too close familiar, because in your basic electronics or your circuits lab, I am sure you have seen this kind of patterns on the oscilloscope in the XY mode. The principle is very much the same. These are called as Lithius patterns. So even there we are looking at the polarization of the voltage, although we don't mention it that way, but the effect is pretty much the same. Now let us consider a special case. Let us put delta as 0. If I put delta as 0, what happens is this term disappears and this becomes, the cos term becomes 1. So therefore I can say that if delta is 0, this equation would become something much more simple. And what would that be? So that would be nothing but Ex square by E1 square minus 2 Ex Ey by E1 E2 plus Ey square by E2 square equal to 0. Now this is a perfect square. So what we can write is, we can write this in the form of a square, which is nothing but Ex by E1 minus Ey by E2, the whole square is equal to 0, which means that Ex by E1 will be equal to Ey by E2, which implies that Ex is nothing but E1 by E2 times Ey. So now what you can see is that the relationship between the x and y components of the electric field is linear, because E1 and E2 are constant. So now what I can say, if I am looking at the xy plane, again I am looking from the z direction into the paper, this is nothing but a line passing through the origin. So something of this kind, where the slope is E1 by E2. So now the electric field vector traces this path. So it is essentially oscillating along a line. That is because we have put the case of delta equal to 0. That is to say, the phase difference between the two electric field components on the two axes is 0. So I am sure you have noticed while observing two waves on the XY mode on an oscilloscope is that the directions, so if the phase difference between the two waves is 0, then the path traced out by the vector is a straight line. This again you have seen on the oscilloscope. Now let us take another special case. Let us assume that E1 equals E2, which is equal to some E0. That is, the magnitudes of the two projections are equal. And the phase difference between the two waves is pi by 2. Now, I am sure if you remember your basic electronics lab very well, you can see where I am going with this. So now if I substitute this on the general elliptical equation, what I will get is this. The cos term will vanish, the cos delta, because cos of pi by 2 is 0. So it is like saying ex square plus ey square equals e0 square. So what is this? This is nothing but a circle. Just like how this time when delta was 0, we are getting that the wave or the electric field vector of the wave is oscillating on a linear locus. This is called linear polarization. So this, when the magnitudes of the two projections are equal and the phase difference between them as a special case is pi by 2, then we get what is called as the circular polarization. Again, we are looking through the z-axis. So what we will get is something of this kind. So the electric field vector may rotate like this, but that's not very important. What is important is the path or the direction of rotation of, what is important is the way the field vector is tracing out. So what you can see is that the field vector, it may rotate this way, anti-clockwise, it may rotate clockwise, but it is tracing out a circle. So therefore this is called as circular polarization. So this is something very, very interesting. In general, the field vector is oscillating, that we all know. But in general, we can see that the way it oscillates need not always be along one axis. Now notice that every time the E field vector is oscillating, automatically the H field vector will also oscillate in a way that is perpendicular to the E field, because that is established. But whatever be the direction of propagation of the wave is still along the x direction, either out or in. That does not change. So this is a very, very interesting result. So now let us look at the directions. Suppose we have a circular polarization. Suppose we are looking at this. Suppose this is the x-axis, this is the y-axis. Now, if my circular polarization looks like this. Now suppose the wave propagates along plus z. So if I am holding my thumb along the direction of propagation of the wave, suppose it is coming out of the plane of the paper, that is on the positive z-axis, then the curled fingers would rotate something of this kind. But right now there is no need to apply the right hand thumb rule, because we are looking at the electric field only. We are not looking at the magnetic field, so that we can just take the product and find out the direction of this thing. So now we have been analyzing vectors using right hand thumb rule. Let us now even put the left hand into operation. Now suppose I am looking at the direction of the z vector the direction of propagation of the wave, which is along the positive z direction, and what I can see is that if the rotation of the electric field vector occupies my curled left hand, that is this way, if this is the way it oscillates, or this is the locus path, this is one option. The other option is when I again have a circular polarization, but if again the wave is propagating along plus z direction, and I am seeing that my right hand is giving the direction of the locus of the E field, which is anti-clockwise. This is clockwise, this is anti-clockwise. Now in general both are possible, but here what we are seeing is that if the polarization follows the left hand thumb rule, then this is called as LHCP, and if the polarization follows the right hand thumb rule, it is called as RHCP. This stands for left hand circular polarization. This stands for right hand circular polarization. So in general both are possible. So I invite you to try an exercise and see what values or what conditions for E1, E2 and what conditions for delta you will get LHCP, and for what conditions you will get RHCP. So in today's class we looked at the solution for wave equation. We saw that interestingly it is very similar to the solution for voltage and current on the transmission line, in particular a lossless transmission line. So on basis of that, just like how we defined that the velocity of the wave in a transmission line is nothing but 1 by under root of LC, we saw that the velocity of a wave in the medium is 1 by under root mu times epsilon. Furthermore, we proved that just like how the transmission line has a characteristic impedance, the medium that through which the wave travels also has an impedance which is called as intrinsic impedance, which is very similar in nature to the characteristic impedance. The only thing is that it is an unbounded medium, but still it has a characteristic or intrinsic impedance, what we call as eta, that is nothing but under root mu by epsilon. So then we moved over, we saw that essentially the E and H field vectors are orthogonal to each other, which are also orthogonal to the direction of wave propagation. And finally we looked at polarization, which is nothing but the direction of rotation or movement or the locus of the E field vector. So we shall continue this discussion when we meet next. Thank you.